My name is Adrian Pope. I'm staff at Argonne, and I actually work on supporting the science applications on the supercomputers at ALCF. And so I'm presenting the Getting Started on Our Systems talk, but this is really on behalf of everybody at ALCF. So I wanted to start with a quick overview of our current systems. So as we mentioned earlier, Polaris is our newest machine. It just came online this summer. And that's what most of the remaining part of this talk is going to focus on. So it's a CPU plus GPU system. It's listed on the top 500. And so there are some numbers for the peak means that's a theoretical peak if you add up all the GPUs and everything. So it's about 34 petaflops. The max is what you can actually do with a real linear algebra application. So it's almost 26 petaflops. It's 560 nodes, and each node has one AMD MILAN CPU and 4 NVIDIA GPUs. So all of the actual compute power is in those 4 NVIDIA A100 GPUs. And our previous large system that's still up and running is Theta. It's a CPU system. It's also listed in the top 500 with a peak of a little over 11 petaflops and a linear algebra max of almost 7. It's 4,392 nodes, and each node has one Intel Xeon Phi or KNL chip. This is sort of a comparison of how much power there are in the GPUs, because we have about 2,000 GPUs in Polaris and about 4,000 CPUs in Theta. And so Theta also has an extension called Theta GPU, which is a smaller CPU plus GPU system. And that was sort of a pathfinder for GPU accelerated computing. It has a peak of around 4 petaflops, and it's 24 nodes. Each node has 2 Rome CPUs and 8 NVIDIA A100s. And then we also have a support cluster called Cooley, another CPU plus GPU system, but its main job is visualization and data analysis, and it has sort of much lower total compute power. It's 126 nodes, each is 2 Haswell CPUs and 1 NVIDIA K80. And then we also have what we call the AI test bed, which is a system that has various AI accelerators. 2 of those are available for applications now, the Cerebrus CS2 and Samanova Datascale, and forthcoming there will be access to several more accelerators. And I think there will be a talk more specifically on that system later in the workshop. So from here on out, we're going to focus mainly on Polaris. So it's our latest computational resource, and this is sort of an on-ramp to Aurora. So this is a large CPU, GPU system where you can really get your applications going, test your frameworks and workflows. It's a generally available ALCF resource, so you can get time on it through the big DOE programs like Insight and ALCC. You can also apply for a smaller director's discretionary allocation to get started on the machine. And so from June 2022, it came in 14th on the top 500. And there's a picture, I think, either before any decals got applied or the opposite side, because this is what it looks like with its decal applied in our machine room. So we're going to go over a bit of detail on what the hardware looks like, so you know how you can go about getting your application to use it well. So the basic node layout, each node has 1 AMD EPYC MILAN CPU and 4 NVIDIA A100 GPUs. And so when it says like the total memory, so each of those GPUs has 40 gigabyte of very fast memory. So aggregate, you have 160 on the node. On the CPU or host side, we have 512 gigabytes of DDR4 memory. So a lot more memory footprint on the host or CPU side. But you can see from the memory bandwidth that you have a lot more memory bandwidth available from the GPUs. So you have really fast memory access on the GPUs. Each node also has 2 SSD storage devices for a total of about 3.2 terabytes of storage. Those are accessible to the user. We'll go over a little bit later how to use them. Currently, each node has 2 Mellanox NICs for accessing the network. And this in total injection bandwidth, and we'll talk about this a little bit more later, Currently, the total bandwidth is 25 gigabytes a second. Later, there will be a hardware upgrade, and each node will have 50 gigabyte access when we get what's called Cassini network interface cards. So to get in between the CPU and the GPUs, it's PCI Gen 4. So you have a data transfer rate of about 64 gigabytes a second to get between the CPU and any of the GPUs. But once you're on the GPUs, then there's NVIDIA's NVLink, which has a much higher bandwidth. So once you get over to the GPUs, you can get in between them very quickly. And at the bottom, there's one measure of sort of double precision tensors. That would be relevant for machine learning type calculations. So the CPU on each node is an AMD EPYC MILAN. Frequency is around 3 gigahertz, so it's what you would expect from a normal workhorse like server CPU. There's 32 cores. Each core has 2 hardware threads, so there's a total of 64 cores, or 64 hardware threads, and I think those present themselves as a separate logical core, but there's only 32 physical cores, so that's good to keep in mind for spreading processes around on the CPU. There's 512 gigabytes of memory, the same sort of memory bandwidth that we saw before. And I think most of the rest of that is pretty standard for server chips. So the NVIDIA A100. So here we have, in the left-hand column, we have the performance of a single GPU, and on the right in this column, it says HGX. This is basically 4 of the A100s bundled together and then accessible over the PCI bus. So on the left, is a single GPU, and on the right is aggregated over 4 GPUs on a single node. So you can see in 64-bit floating point, you have almost 10 teraflops per card, so almost 40 teraflops in the HGX. You get twice that in single precision, so 20 teraflop per card and almost 80 teraflop total. And then when you see like the tensor core operations, so those are either specialized or lower precision operations, and there you can actually achieve even higher flop rates. So that's very relevant for people doing sort of machine learning reduced precision calculations. So there's quite a bit of potential compute in these. And each GPU has 40 gigabyte of very high speed memory, so a total of 160 per node across all of them. And the memory bandwidth getting from that memory is 1.6 terabytes a second per GPU. And then the interconnect, yeah, it's PCI Gen 4 to get to any of the GPUs, and then in between you get NVLink at 600 gigabytes a second. So the node local storage. So each compute node has 2 SSDs. They're 1.6 terabytes each, and so 3.2 terabyte total. This is very similar to each node on Theta, our current, one of our previous systems. There's no specific software for using the SSDs. They're put together in a RAID 0 volume, and it's basically presented as a file system. So you can access it it shows up as the directory local scratch, and you can read and write to that storage in any POSIX method. It is very important to know that data is destroyed on this when the job ends. So you can use it as a temporary store during your job. If you want to keep any of the information that's on the node local storage after the job is done, you need to copy it out to one of the permanent file systems, one of the shared file systems. So there's a really good interconnect on Polaris. It's Cray HP's Slingshot Interconnect. So these have really interesting new switches called Rosetta switches. They support what's called multiple quality of service levels. So packets from different kinds of operations can be given different priorities. There's really aggressive adaptive routing and congestion control. And the goal here is to get both very low average and tail latency. So sort of very quick to get from any point on the network to any other. And it has high performance operations for multicasting and for reduction. And so here is where we're going to talk a little bit about the future hardware upgrades to Polaris. So currently, the interconnect is Slingshot 10. And I think this is largely just the network interface card that's on each compute node. So currently it's Slingshot 10. This is a Mellanox Connectix NIC. It supports the HPE Cray MPI stack. It's sort of Ethernet functionality with RDMA offload. And this is 100 gigabits for each NIC. So the numbers in the upper right are for the entire machine in aggregate. So the current state with Slingshot 10 and the 100 gigabits per network interface card, the total injection bandwidth across the system is 14 terabytes a second, and the bisection is 24 terabytes a second. Now, at some point, I think either later this year or early next year, the plan is to upgrade the NIC on each compute node to Slingshot 11. So this is called the Cassini NIC, and this is a very high performance network interface card. Not only does it increase the bandwidth to 200 gigabits per second on each link, it also has features like MPI hardware tag matching, an MPI processing engine, supports more one-sided operations, optimizations for collectives, and this twice the injection bandwidth. So when those get replaced in each compute node, then for the whole system, the injection bandwidth will essentially double to 28 terabytes a second. The bisection will stay the same because most of the rest of the network is remaining the same. So that'll remain at 24 terabytes a second. So this is a brief overview of what the network topology is. So the machine is organized into Dragonfly groups. So there are 11 total groups. There are 10 compute groups. Since we have 560 compute nodes total, each of those compute groups has 56 nodes. And we have one non-computer service or support group. And so that service or support group is sort of, that's where all the traffic goes to get to the shared file systems and other things like that. And the diagram above shows there's basically 200 gigabits between each group. And then within each group, there's 400 gigabit connections between each of the routers. So there's sort of more bandwidth available within a compute group. So if you have a small job, if you stay within a compute group, you'll get a bit higher bandwidth. But when you go out to a very large job that crosses groups, then you'll have access to even more routers as well. And in the bottom is a node again, currently 100 gigabits for each NIC, and that'll be upgraded to 200. So the total system configuration. So there are 560 compute nodes, so that's 560 CPUs. It's 2,240 total GPUs. The total amount of GPU memory across the entire machine is almost 90 terabytes. The total host memory is 280 terabytes. And then if you use the SSDs, there's a total of 1.7 petabytes of storage on the machine itself. The interconnect is this HPE Slingshot. There's 2 NICs per node, so 1,120 NICs, 80 switches. Total injection bandwidth, as we said earlier, currently about 13 or 14 terabytes a second, will be upgraded to 28, and a total system power of 1.8 megawatts. So storage. So Polaris is connected to existing ALCF storage resources, and the 2 largest of those are Grand and Eagle. So Grand is the main global or center-wide file system. It is 100 petabytes of storage with a maximum I/O rate of 650 gigabytes a second, and this is accessed through the Lustre LNet routers, which are part of the Polaris gateway nodes in that 11th service group. Eagle is essentially the same file system, so another 100 petabytes at 650 gigabytes a second. But this is what we call a community file system. So it is sort of hardware-wise very similar, but it also is more connected to the outside world. So you can get data to and from Eagle using like Globus file transfer. So if you have a project where you really want to share a lot of data with people outside of ALCF, then your project can apply for space on Eagle, and that makes it easier to share with the community. So the gateway nodes from Polaris can provide more than 1 terabyte a second of total throughput. So that's to try to match the total that you could theoretically get from both of those large file systems. There's also a relatively small shared home file system. So when you log in your home directory, that should be the same on all ALCF machines, all of our main ALCF systems. And it's small and not particularly fast, but that's where you can keep all of your configuration files and such so that your account looks the same on all the machines. So now we're going to talk a bit about the software that you use on Polaris and how to use the software. So first, you need an account to get on Polaris, which probably everybody, or hopefully everybody here has done. So you start that out by going to the accounts.alcf.anl.gov website. Then you also need an allocation or a project to run. And so these can be like the big DOE types like Insight or ALCC, or ALCF also has these directors discretionary accounts, which are smaller allocations for getting started on the machine. And the name of the resource is Polaris. So to connect, you can SSH and then your username at polaris.alcf.anl.gov, and then your password is going to be 2-factor. So it's a PIN and a one-time password from a token. Okay, file systems. So as we said a few slides ago, the shared common /home with all the other ALCF systems, that's where you will be in your shell when you log in. The Eagle and Grand file systems are mounted in /lus/grand and /lus/eagle. And your main project storage will be something like lus grand projects and then the name of the project. Or if you have a project that wants to share a lot of data with the outside world, it'll be in lus eagle projects and then the project name. And so when you start actually, reading and writing a lot of data, doing things that really depend on high performance IO, you definitely want to be running out of one of the project directories and not out of your home directory. And also, we don't have with Polaris a separate concept of scratch storage. So like all the storage in the project directory, that's all the storage that you have for working on Polaris. So like that's the high speed, that is the permanent storage. So you basically don't have to copy things around. So for controlling your programming and software development environment, we use a system called modules. The particular variant we use is called LMod. And that interfaces really well with all of the HPE Cray software, as well as all of the software that ALCF provides. So this will be automatically loaded when you log in. So if you type module list, you'll see what modules are loaded, and several are loaded by default. If you want to load a new module to change something about your software development environment, you'll say module load and then the name of the module. There's also unload if you want to take that out of your environment. A really important one is module avail. So if you type module avail, that will show you all of the modules that you could currently load. And that's really useful to be able to see and sort of use grep and figure out what's there. There's also this module use and then give it a path name. So by default, you'll have at least one directory of module configurations loaded into this path, but say you want to use some software that's been set up on the side, you can use module use and put in an alternate path, and then this is a way to make even a larger or different set of modules available. And so on the right is, I think this is at one point, this would have been the default modules that you would see when you log in. And it's interesting to look at what a few of these are. So let's start out with the sort of PRGENV. So that's your programming environment, that's second from the bottom. And so this shows that the programming environment is this NVHPC or NVIDIA's HPC environment. So this sets up essentially what compilers will be used by default. And all of these like there's like cray-mpitch, so that's showing that the HPE cray MPI will be the MPI that's included with some of the compiler wrappers, and so that's the high performance MPI that you want to be using to make the most of the network. And then the first module, I guess they're numbered. That's great. So module 1 and 14, those are also really important. So these are setting up the architecture targets for the compilers. So the first one, this cray x86, cray PE x86 Rome. So that's setting up the CPU target. So it's going to be targeting the Rome architecture. And I think it's still pointing at Rome because there were some issues when trying to use the specific settings for the MILAN CPUs. So I think right now it's set back to Rome. But I think when those details get worked out, the default will probably change and eventually point to the MILAN specification. And then the last one, the cray PXL NVIDIA 80, that's pointing at the architecture for the A100. So this is really important. It's nice to take a look at this, do a module list, make sure that the compilers are set up to compile for the target architecture of the Polaris compute nodes. So compiling. So the basic part of compiling is wrapped up in the cray programming environment. So HP provides compiler wrappers, which by default include a lot of libraries that are going to be useful for running on Polaris, mainly the MPI libraries. As I said before, it's integrated with the modules environment. And this is basically a clean way of including a bunch of flags to include the right headers, the right libraries, the correct compiler options for the target architecture and linker options. And so this is normally, for convenience, hidden in some compiler wrappers. If you actually want to see every single command line flag that's being used by the compiler and linker, you can throw this -cray PE verbose flag, and that'll help you see what is exactly getting sent to the compiler and linker in case you need to debug or slightly tweak that. So the default programming environment on Polaris is PRG and NVIDIA. And so the sort of lowercase cc, uppercase cc, and FTN, these are the compiler wrappers that cray HPE provides. So these are the actual names of the compiler executables that you'll want to call. And so when you have the NVIDIA programming environment loaded, lowercase cc will point to NVC, uppercase cc will point to NVC++, and FTN will point to NV Fortran. And these compilers support both CUDA and OpenMP target offload. When you have these loaded, the NVCC or the NVIDIA CUDA compiler is still available, but it's not going to be called directly by the CC or FTN wrappers. And we also have some programming environments for other compilers. One popular example is the GNU compilers. So if you unload the NVIDIA programming environment and load in the GNU programming environment, then the CC wrappers will point to GCC and G++, and FTN will point to G Fortran. But the real advantage here, the way the system works and why it's convenient, is you can use these programming environments to set which base compiler it's pointed at. But then when you call the wrappers, this is the part that's including all of the flags that you need for MPI libraries. So that can keep the sort of make systems looking pretty clean. And then all of the libraries are going to be found in either /op NVIDIA or /op cray for all of these SDK libraries. So running jobs. So running jobs on Polaris, there's sort of two layers that you want to think about. First is interacting with the scheduler. So that's how do you get a job into the queue? And the queue is going to keep track of all the jobs that people want to run and figure out when to actually put them on compute nodes. And once your job actually starts, then you need to launch your actual MPI job onto the compute nodes. And that's done using something like MPI exec. So when you write a script it's going to be a script that you submit to the scheduler, and you want to describe the parameters of your job to the scheduler. Somewhere in that script will be a line with MPI exec to actually start your job. This is a little bit different than on our previous system beta, but the scheduler script actually runs on one of the compute nodes in your job. So it's sort of, when your job launches, one of those compute nodes will be picked to run the shell script. So you can put anything you want in the shell script and it can run on the CPU or GPU. You want to make sure that you load any modules that might not be a default part of your environment in the script before it calls the MPI exec. And then let's say you called your script run.sh to actually submit it to the scheduler. You would do q sub -q, and then prod here is the production queue, and then the script run.sh. So this will basically tell the scheduler, hey, there's the script that we want to put into the queue to run later. When it returns, it will return job ID, which you can use to find information on that job, where it is in the queue or if it already ran. And then output and error logs will be written into the directory where you submitted the job. So on the right-hand side is the possible contents of this example run.sh script. So at the top, bin bash, it's just a bash script. So anything you can do in bash, you can do in these scripts. So if you know bash, you can feel free to put whatever fancy scripting in you would like. The top, these hashtag PBS lines. So these are the lines that are communicating information about the job to the scheduler. So the top -A, that's what allocation we want to use. So here you can put the name of whatever project name you have for your allocation. The -L wall times, this is saying we want to run this job for an hour, up to an hour. -L select in this case would be, I want 4 nodes. -L system, Polaris. So the scheduler we use can potentially schedule jobs on multiple systems. Right now, it's only connected to Polaris. So this is kind of the only option right now, is to say -L system Polaris. But it is possible in future to perhaps co-schedule jobs between systems. And this -L system is where you would specify the name of the system. This last flag, this -L file systems, this is actually important for our systems. So we talked earlier, there's a home file system and Grand and Eagle. And it's important to specify which file systems your job actually needs to use. And it's important because there can be different maintenance periods or different availability between the different file systems. So they say that Grand is under maintenance. If you've specified in here that you only need home and Eagle, then the scheduler knows that this job can run even though Grand is offline. But let's say that there's some maintenance happening on Eagle and that's not available. Then this tells the scheduler, no, this job needs to wait until Eagle is available again. So this way your job doesn't get run when the correct file system isn't available. So I think this probably was optional on Theta. I think it might be required on Polaris. And then the next few lines are essentially bash. So you set RPN to 4. So this would be if you wanted to run 1 MPI process per GPU, you would want to run 4 ranks per node. You can do bash math. So in this case, the scheduler, which is PBS, will set an environment variable PBS_nodes. This tells you how many nodes your job has. So you can do this bash line to multiply the number of nodes by the ranks per node to give you a total number of ranks. This next line is actually very important. So the shell that is running this job script does not start off in the directory where you submitted the job. So if you're not, I think you'll by default show up in your home directory. So you need to put in some sort of change directory command. So if you do this cd to pbso workdir, that will take you to the directory where you submitted the actual job script, or you could put in a fixed path if you're working out of directory and you know the absolute path. After that, you can do something like module load if you need to load a non-default module. This set plus X, so this basically will cause the shell to be very verbose after that. So this is good for tracking if you want to see all the commands that were submitted and then all of the values substituted for debugging later. Pardon me. Then you can set plus X. So env, that'll just print out all your environment variables. That'll be good for debugging later. And then the last line is the actual like launching of the MPI job. So MPI exec -n, and this procs, that'll be the total number of MPI ranks for the job. PPM is processors per node. So you do RPN, which in this example is 4 or 1 process per GPU. CPU bind core, that sets some affinity between cores and ranks. This -g env all, that will transfer all of your environment variables to the executing job, and then the name of your command and some options. So the schedule we use on Polaris is PBS Professional. If we have users here who have been on ALCF systems for a while, this is a change from our previous systems. So our previous systems ran the Cobalt scheduler, and Polaris runs PBS, and I think our systems moving forward are also going to be running PBS. So it has very similar looking commands to our previous scheduler, though some of the flags may have changed. So queue sub is how you submit a job to the queue. So this requests resources, and your script will be started on the head node of the job once it starts. Common options for this, -A is your allocation. -L will communicate options like number of nodes or system. -I you can use to indicate that you want an interactive job. And -Q will say which queue to submit to. This could be something like a debug queue or a production queue. Queue stat will show you the status of the queue, so you can check on the status of the jobs that you've submitted. If you give it a -Q, that'll actually list all of the queues. So it won't list jobs, it'll just list what queues are available. If you want to see more detailed information on a job, you can say -F and then the job ID. If your job is already completed, it won't show up in the current queue, the list of currently queued jobs, but you can say -X, and that can look through the logs for information about jobs that have already completed. If you've already submitted a job, so you've already done queue sub on a job and you want to change something about it, you can use queue alter to update the job parameters. If you've decided that you don't actually want that job to run anymore and it hasn't run yet, you can run qdel to delete it out of the queue, or if the job is currently running and you issue qdel, it will stop the job. So how you specify resource requests and placement. So there are some job-wide options, like you say -L wall time equals 6 hours in this case, so that's an option for the entire job. Resource selection, so this is where you specify, how many and what kind of node configurations you want. So a simple example of that, and this will suffice for most things that you would want to do initially on, say, Polaris. So this example, if you want to do 128 compute nodes on Polaris, you do -L select equal 128, colon, and then system equal Polaris. So this is saying I want one set of 128 nodes on Polaris. And then, and there's a lot more documentation about exactly how you set these resource parameters. It's useful to be aware of a few definitions. So chunk is the set of resources allocated as a unit to a job. So in a lot of cases, a chunk will just be a set of Polaris nodes. And a V node is a virtual node. This is technically an abstract object representing a usable part of an execution host. I tend to think by default, a V node could be an entire compute node, but you could also split up a compute node into several subnodes. So if you wanted to have one virtual node for GPU, you could split one Polaris compute node into 4 V nodes, and then treat each of these as the separate entity that's running one MPI rank. And CPUs, so on Polaris, this is going to be equal to the total number of hardware threads. And since Polaris, each node is a single socket, and that has 32 cores with 2 hardware threads, and CPUs equals 64, is sort of how the hardware, the NCPUs will be presented through PBS for Polaris. And GPUs, so this is the number of GPUs. Generally, this will be 4, though if you want to use MIG or multi-instance GPU mode, this could be a larger number. Some useful commands for working with PBS. So if you had worked on our systems before, like Beta and Cooley, and you know a lot about writing Cobalt scripts, there is a script called qsub to PBS, so you can give it a Cobalt qsub command or script, and it will return the PBS equivalent. So if you have a bunch of old scripts and you want to get a quick start on what those would look like in PBS, you can use that translator. There's also a command called PBS nodes, which will show you a list of the nodes and their current states. So you can see what's up, what's down, what's running jobs, what might be rebooting or something like that. So queues. So Polaris has 3 main queues. There's a link on these slides, which I'll post in Slack after this is done, detailing what queues are available and what all the parameters are. But basically, the 3 most common ones are going to be debug, which is meant to run a very small debug job for up to an hour. There's debug scaling, which is if you want to run a slightly larger job that's still short. So this is if you want to run a few nodes, but again, very short, and you can't submit very many of these jobs at once. But once you sort of debug your jobs, then you go to the production queue. And so for the production queue, right now, you need to use at least a minimum of 10 nodes. You can use up to a maximum of 496 nodes. I think as of yesterday, the minimum job time is 5 minutes, and the maximum job time will be either 6, 12, or 24 hours, depending on the size of your job. So basically, Polaris is intended to be a resource to run really large jobs. So the structure of the queue is intended to promote projects to try to scale up and run larger jobs. So you'll get access to more and more wall clock the bigger your job is. And this node at the bottom, prod, is actually what we call a routing queue. So there are actually separate execution queues for different job sizes to get these different wall clock limits. But if you just submit to the prod queue, then the scheduler will look at your job parameters and figure out which execution queue it should actually go to. So as a user, you basically only need to interact with prod. But then if you look at the list of jobs, it's good to know that that one was actually just routing to another set of execution queues. So running MPI applications. So as we said before, the jobs run directly on the compute nodes. This MPI exec command runs applications using the parallel application launch service. So MPI exec has a bunch of different command line options. The most common ones here, -n's total number of MPI ranks. PPN is the number of MPI ranks per node. There are flags for CPU binding, and depth is basically setting how many CPUs you want per rank. Env is a way to set a particular environment variable. There is also the -g env all is just send all from your shell environment. And then host file. So I think by default, you don't need to specify a host file, and MPI exec will just say, great, all of the nodes that were available for this job is the set that I will use to run. But say you want to split up and run different sub jobs as part of one big job to the scheduler, or select particular nodes, you can always do host file and specify a list of particular nodes in the host file and pass that to MPI exec. So for a full list of options, you can look at the manual page for MPI exec. You can also look at the examples on our web documentation. And for specifically for Cray's MPI, if you want an introduction to Cray's MPI, and specifically, you can, on the command line on the Polaris login node, you can say man MPI intro, and that'll show you flags and options for Cray's MPI. So a quick blurb about Python. So the Cray PE means programming environment. So the Cray programming environment does include several Python modules, or several, this is where the word module get a little confusing, but it has some of the popular Python modules, and this comes as part of the Cray-Python lmod module. So if you say module load Cray-Python, you'll get access to Cray's build of NumPy, SciPy, Pandas, and MPI for Pi. And I think there will be more talks later specifically about using Python on Polaris. So debugging and profiling. So there are several debuggers available on Polaris. There's Stack for stack trace analysis tool. So if you have a big MPI job and you need to do a stack trace on it, you can run the stat tool. GDB for HPC is sort of an MPI parallelized version of GDB. And I think that will show you things about the sort of CPU side of a job, but not necessarily. I'm not sure if it does CUDA specifics. There's CUDA GDB, which is NVIDIA's specific tool for debugging the CUDA parts of the code or what's running on the GPUs. And then there's also standard GDB if you want to do something like debug the host on a single node. So for profilers, there's the performance analysis tool, or PAT. And so that will be a profiler for sort of the MPI and CPU part of the job. If you want to do performance profiling specifically of what's running on the GPU, you can use NVIDIA's Nsight tools, and that'll give you really good performance analysis on the GPU. So for information and help, so basically user documentation, we have a lot of it existing and we're adding to it all the time. So that's at alcfanl.gov/support center. There's a specific page. If you go to alcfanl.gov/Polaris, that'll give you a Polaris specific page in our documentation. And then there's also always the support ticket system at ALCF. So if you're having trouble with your account or need to figure something out in our systems, you can always email support@alcf.anl.gov. And with that, we are to the end of the getting started.